Okay, welcome to another talk of the virtual seminar on geometry with symmetries. It is a great pleasure to introduce Valeria Gutiérrez from Universidad Nacional de Córdoba in Argentina, that will talk about stability of generalized Einstein metrics on aligned homogeneous spaces. Thank you, Valeria.
Thank you, Emilio. First of all, I would like to thank the organizers for the invitation. Thank you so much for this opportunity. The talk is going to be broken into three parts. First, we are going to see the definition and some examples of aligned homogeneous spaces. This is a definition from Jorge Lauret and Will. And we are going to stay in the case when the Lie group acting on M has two simple factors, G1 and G2. Then I'm going to show you the definition of generalized Einstein metrics, mostly known as Bismuth-Ricci flat metrics, and diagonal and non-diagonal Einstein metrics on M, and some results obtained by Lauret and Will on these aligned homogeneous spaces. To study the stability of these metrics, it turns out that the Bismuth-Ricci flat metrics are the fixed point of the generalized Ricci flow studied by Garcia Fernandez and Streets. So I'm going to show you the dynamical stability of these metrics. And for the diagonal and non-diagonal Einstein metrics, I am going to present the stability with respect to the Hilbert action. So to start, an homogeneous space M is determined by the Lie groups G and K, of course, but also by the way K is embedded into G. So to see some invariant of this, we are going to consider a homogeneous space presented as G over K, where G is a compact semisimple Lie group and K a closed subgroup. And we consider these fixed decompositions of the Lie algebras G and K. Here, G1 to Gs are the simple ideals of G, the same with K, where K0 is the center of the Lie algebra K. Each set in the Lie algebra K, we can see them as a vector of S components, where each set Y is the projection of set into GY, considering this fixed decomposition. So, if we restrict this projection into Kj, we obtain that it is an isomorphism as soon as the image is different than 0. So we have that Pykj is a simply subalgebra of Gy. So for all y and j, there exist constants Ayj such that the Killing form of this subalgebra Pykj is equal to these constants multiplied by the Killing form of the Lie algebra of Gy restricted to this subalgebra. And these constants Ayj are invariants of how K is embedded into G. So an aligned homogeneous space is as homogeneous space as before, G over K, where G has a simple factor and K has T simple factors with a center. It's going to be called aligned when there exist positive constants, one for each factor of G, such that satisfy this condition, this alignment property with the Killing constant. I defined it before. Here we have a lambda j for each factor of K, for each simple factor of K, and an aligned homogeneous space satisfies this equality. Also, for the center of the Lie algebra K, we have we ask to have an inner product satisfying this equality. Here there are the disaligned constants again. And the third condition is just a normalization with these constants to define them properly. So in particular, for these aligned homogeneous spaces, we have that the Killing form of the Lie subalgebra Kj is equal to lambda j multiplied by the Killing form of G restricted to Kj. And for the center, something similar occurs with this inner product. Another way to define these homogeneous spaces is considering the third cohomology. These are the spaces with the richest third cohomology, which means that if G has S simple factors, the third Betti number of M is equal to S minus 1. For the rest of the talk, we are going to consider S equal to 2. So G has only 2 simple factors, and the Lie algebra is given by G1 plus G2. So the definition is the same. Here we have a pair of Killing constants and satisfy this equality, this alignment property. Consider lambda j. Here K is not simple and it could have a center. So we have a T lambda j, one for each factor of K, and the normalization about the aligned constants. To see some example, for example, if K projects non-trivially on each G1 and G2, and it is simple or one-dimensional, then we have that the homogeneous space M G over K is aligned. Therefore, any pair, if we have an homogeneous space G1 over K and G2 over K with K simple, determines an aligned space. This is because when K is simple, we only have one lambda, so we can define these Killing constants that define all the conditions of the definition. Another example to generalize a little bit more this, we can consider two homogeneous spaces, M1 and M2, where each Gy is simple, and satisfying this property with respect to the Killing forms. Here K is not simple, but the Killing form of K is equal to a multiple multiplied by the Killing form of Gy restricted to K. We have different multiples for each Gy. So with this setting, we can consider the aligned homogeneous space M, where the aligned constants are given by C1, C2, and all the lambda are equals to A1 multiplied by A2 over A1 plus A2. So with this setting, we can always have an aligned homogeneous space. If we assume that A1 is less than or equal to A2, we have, because of the normalization of C1 and C2, we have these restrictions to them. So in this setting, we can define G equal to G1 times G2, and we consider its reductive decomposition orthogonal with respect to the Killing metric G, K plus P, and we fix the J-invariant standard metric now on the homogeneous space M, given by the Killing form of G1 restricted to P plus the Killing form of minus the Killing form of G2 restricted also to P as a background metric. And we consider this decomposition into K invariant subspaces of P and orthogonal with respect to this standard metric. Here, each Py, P1, and P2 are equivalent to the isotropy representation of these previous homogeneous spaces My, and P3 is given by this subspace. Here, there are involved the aligned constants, C1 and C2. It could also be in terms of A1 and N2. This decomposition is much more complicated when G has more simple factors, because we want this decomposition to stay GB orthogonal and not K invariant. So when S is equal to 2, it is hard enough. And here P3 is equivalent to the joint representation of K.
Valeria,
To start, yes.
one small question. In this slide, are you assuming K simple or might be?
No, not necessary. It is an example, but we are only asking that this this restriction about the Killing forms to state the same multiple for each simple factor of K.
Is this equivalent that the equation is Einstein or not related? No. I confused.
No,
Sorry.
no, it's just how K is embedded into G.
Okay, thank you.
we are asking, yes, some kind of alignment that each factor of k is embedded similar with the same constant. So to start with the bismuth,
Could I ask
yes,
a question?
yes.
So in P3 there, so is Z1 the projection of Z bar onto, sorry.
Yes, sorry. Here C1 is a projection of Z into G1.
Yeah.
Because here we are seeing this as in G and G1 plus G2. Yes, okay. So to start with the generalized Einstein matrix or bismuth-Ricci flat matrix, I am going to present the bismuth connection. In general, given a compact Riemannian manifold Mg and a three-form H on M, the bismuth connection is a unique metric connection with torsion T satisfying this equation. And if H is a closed three-form, then the pair Riemannian metric and three-form is called a generalized metric. A natural way to make this structure evolves is considering the generalized Ricci flow, which evolves these structures in the direction of the Ricci tensor of the bismuth connection. This generalized Ricci flow was studied by Garcia Fernandez and Streets, and it is given by these equations. The first equation, flow symmetric, and the second, the three form. And the fixed point of this flow are the bismuth-Ricci flat metrics, also called generalized Einstein metrics, which are those metrics, a Riemannian metric and three form, such that the three form is always G harmonic, and the Ricci tensor, here is the Ricci tensor with respect to the Levi-Civita connection of G, is equal to the H square, which is a symmetric two tensor non-negative. When these two conditions are satisfied, we obtain a bismuth-Ricci flat metric, which are the equilibrium point of this flow. So to go again back to the aligned homogeneous spaces, we had M with G with two simple factors satisfying this condition about the killing metrics. We have the reductive decomposition and the add K invariant decomposition of P into add K invariant subspaces. And here. Lauret and Will proved that the closed tree-form H0 given by this equation, here Q is a bivariant symmetric bilinear form given by this. Here A2 and A1 are this constant relative to the killing forms. When H0 is defined as this, and here this is the projection of the Lie bracket into K. We obtain that this tree form is G harmonic for any J invariant metric of this form. We are going to call diagonal these metrics because they have a factor on each restriction of the standard metric into each add K invariant subspace of P. Lauret and Will prove this theorem. They found bismuth-Ricci flat metric on any of these spaces given by H0 and G0, which is here. And furthermore, this is the only J-invariant bismuth-Ricci flat generalized metric on M of this form, if we have a diagonal metric and the closed reform H0. In fact, this theorem is a little bit more general because they found a bismuth-Ricci flat on any metric on any aligned homogeneous spaces. This condition is not required, so the metric is given in terms of C1 and C2. But for now, this is going to be the setting. So to study the generalized Ricci flow, to see the dynamical stability of this fixed point, we are going to assume one more condition, that each homogeneous space My has its standard metric Einstein. There are a lot of examples holding this condition, 17 families and 50 isolated examples of homogeneous spaces. So we keep that we have examples of this. So we are looking for invariant solutions to the equation given by the generalized Ricci flow. So we define this metric GT, where we have smooth positive functions on each factor, real functions, x1, x2, and x3. And we know that H0 is GTR harmonic because it was harmonic for any diagonal metric for every t, for every positive t. So the second equation, that which flows the three form, vanishes, and starting from some generalized metric of this form, we have that the generalized Ricci flow in this case is only given by the first equation. A lemma explaining why we keep with the diagonal metrics given, or why we assume these conditions. Given these assumptions, the set of diagonal metrics with respect to this decomposition in at K invariant subspace is invariant under the generalized Ricci flow, meaning that if you start with a diagonal metric, the flow gives you again a diagonal metric. So, in terms of dynamical systems, the generalized Ricci flow for metrics of this form can be given of a system of ODEs. Here X represents the smooth functions that flow the metrics, and F the equations given by the flow. So we have an equilibrium point of this system, we have a fixed point, so we know that in this bismuth Ricci flat metric, this function F defining the flow vanishes. And if we want local properties of this flow, we can study the linear system given by the derivative of the function at G. Now I want to show you the equations of this flow. Here, F1, F2, and F3 are the component of the function F defining the flow. So we have the derivative of x1 equal to F1, sorry, the derivative of x2 equal to F2, and so on.
Vale.
Yes.
We are not seeing another file.
Oh, too bad. Okay. Now, yes.
Yes. Now
Great.
we can.
Thank you, Romina. So I was saying that these are the equations which define the flow. Here F1, F2, and F3 are the coordinates of the function F. So the derivative of the smooth function x1 is equal to F1, and so on with the others. Here there are involved, of course, a metric, x1, x2, and x3. And these scaling constants corresponding to the homogeneous spaces M1 and 2, and these K1 or kappa 1 and kappa 2 are some constants relative to the Casimir operator. When we ask the homogeneous spaces My to have its standard metric Einstein, that implies that the Casimir operator of the isotropy representation of My with respect to this killing form restricted to K is a multiply of the identity. So these kappa 1 and kappa 2 are those multiples. That's why we ask for this condition, and that's why we have the diagonal metrics invariant under the flow. So here, let me run this. And here we can check that the metric given by these coordinates is a fixed point of the flow. We have those zeros, F vanishes when we evaluate it at it. So you are seeing again the beamer?
Yes.
Great, thank you. To study the flow, we can we look for invariant subspaces. We want to see some plots. So we realized that the plane given by x3 equal to a1 plus a2 over a1 is invariant by the flow. And when kappa 1 is equal to kappa 2, this plane is also invariant. So when we have this invariant subspace, we can see plots in two dimensions. So let me show you. Well, here is only to have the equations. We are going to consider the example when M is the 55-dimensional subspace given by SU7 times SO8 over SO7. Here we have the condition, K is simple, so A1 is equal to 5 over 14, A2 is equal to 5 over 6, and kappa 1 and kappa 2 are both equal to 1/2. The Bismuth-Ricci flat metric is given by this, A1, 7 over 3, 10 over 3, and the plot we have is this. This point is the Bismuth-Ricci flat metric, and it seems that the flow is going there. It seems that this fixed point is an attractor of the flow, at least considering diagonal metrics and this plane. If we go for the other, in this case, we have kappa 1 equal to kappa 2, so we can consider the other plane too. And the plot is similar. This point is the Bismuth-Ricci flat metric, and in this plane also, all the flow is going there. It seems to be an attractor of the flow. So that's what we proved. In this setting, an aligned homogeneous space is such that we have this condition of the Killing forms, and each homogeneous space in M1 and M2 has its standard metric Einstein. We see that G0, this Bismuth-Ricci flat metric, is asymptotically stable for the generalized Ricci flow, meaning that if you start near enough the metric, the flow, you go to the Bismuth-Ricci flat metric by the flow. When we consider G1 equal to G2, we call it H. The Bismuth-Ricci flat metric is given by this, and we could prove that any diagonal generalized Ricci flow solution converges to the Bismuth-Ricci flat metric, meaning that it is globally stable. No matter how close or not you are from the metric, you can you end there after the flow. So just a remark about why we consider diagonal metrics. If M is multiplicity free, which means that both homogeneous spaces are isotropy irreducible and K is simple, and the representations are in equivalence, the diagonal metric are in fact all the J-invariant metrics on the homogeneous space M. And to say something about the proof of this theorem, the first condition is a local property, so we can study the behavior of the linear system given by the derivative of f in the fixed point. This is given by these metrics, so we have that all the eigenvalues of the metrics are real and negative, and this implies that the equilibrium point is asymptotically stable. When we wanted to prove a more global condition, we found out that it is much more complicated due to the possibility of chaos. A way to prove this is finding a Lyapunov function, which is a continuously differentiable positive defined with a negative defined first derivative with respect to time along all straight trajectories. If we found this, a Lyapunov function, we could prove that if we find this, we can prove that the fixed point is in fact globally stable. We consider this function. It seems nice. It is, of course, positive and differentiable, but when we consider its first derivative, it was very hard to prove that it is negative definite on all diagonal metrics. So that's why we could also prove it when G1 is equal to G2. We have only one A here, and we can conclude that the derivative of this function is negative definite. So the theorem holds. Any questions? As for?
I
Okay.
have a question, Valeria,
Yes.
about the remark from previous slide.
Yes.
It's very simple. In the case G1 equal to G2, it is not multiplicity free, right?
No, you never have it.
And it is an if and only if, or not? There might be G1 different to G2 and not multiplicity free.
It depends on K, right? Because you can have K non-simple, for example.
Okay.
Yes, I think you have to check all the conditions. Maybe P1 and P2 are going to be inequivalent, but you have to check what happened with K.
Okay, thank you.
Okay, so with this, I finished kind of a second part of the talk about generalized Einstein metrics. For the rest of the talk, we are going to stay in this case, Emilio said, when G1 is equal to G2, we are going to call this Lie group H. And we asked now H over K to be an irreducible symmetric space such that it holds this condition about the Killing form. And well, this is a dimension of K. So we consider the aligned homogeneous space again of dimension 2n plus t, given by h times h over delta k. Here, delta k is the diagonal embedding because we have that G1 and G2 are equal. And as before, we consider the G, the Lie group H times H, and here is the reductive decomposition of the Lie group H, orthogonal with respect to its Killing form. So the reductive decomposition of M, orthogonal with respect to the Killing form of G, is given by delta K plus P, where delta K is the diagonal with respect to the Killing form, and P is decomposed as before in a K invariant subspace. P1 and P2, they are related to the reductive decomposition of H. And P3 is given by this equation. If we remember the first definition of P3, it was involved the align constants C1 and C2. Here they are equal, so we only have minus z in the second component, in the projection of z into each h. So as at K invariant representation, P1 is equivalent to P2, equivalent to the isotropic representation of H over K. So we have that M is never multiplicity free in this case. And P3 is the adjoint representation of K. It's equivalent to the adjoint representation of K. So this equivalence of P1 and P2 allows us to introduce a non-diagonal invariant matrix. We are going to denote them as this vector x1 to x4, defined by a multiple on each factor when we restrict to P1 times P1 or P1 times P2. And when we restrict to P1 times P2, we have this x4. This condition on this constant defining the matrix are just to make it positive defined. These metrics are going to be called diagonal when x4 is equal to 0. And if we see a representation of this metric as a matrix with respect to the standard metric on M, we see this. That's why when x4 is equal to 0, we have diagonal metrics. Here I is the identity, n is the dimension of h over k, and d is the dimension of k. So we can define metrics of this form in these homogeneous spaces. We called M4 the subspace of all invariant metrics of this form, and they are in fact all the invariant metrics on M if the isotropy representation of h over k is irreducible of real type and k is either simple or one-dimensional. So for the rest of the talk, this is our setting. We have an homogeneous space M given by h times h over delta k, and these metrics which are going to be called diagonal when x4 is equal to 0, and if not, we have non-diagonal metrics. Lauret and Will studied very recently when these metrics are Einstein on M. So in fact, they studied more general when h times h over delta k is any homogeneous space, is not necessarily an irreducible symmetric space. So, but in the case when h over k is an irreducible symmetric space, they obtain a complete classification. So in this case, when we have the condition about the Killing forms, they prove that the h times h invariant Einstein metrics on M are given by, sorry, G1 and G2. These metrics are diagonal. X4 is equal to 0, and they exist when A is less than 1/2. A is this factor here concerning the Killing forms. And if A is greater than 1/2, they obtain non-diagonal metrics, Einstein metrics, given by these equations. But they also found that these metrics, G5 and G6, are Einstein on any M, no matter the condition about the Killing forms of if A is greater than or less than 1/2. G5 and G6 are Einstein on any homogeneous space M. Here, G3 and G4 are isometric, G5 and G6 too. Here, the isometry is easy, it's just exchange the factors H. And G1 and G2 are non-isometrics. So according to this condition, an homogeneous space like this can have 2 diagonal metrics and 1 non-diagonal up to homotecities. Or it can have 2 non-diagonal Einstein metrics. So Lauret and Will listed these irreducible symmetric spaces where the condition holds, the condition about the Killing forms. The table includes 5 infinite families and 5 sporadic examples. Among these, there are 3 infinite families and 2 sporadic examples where A is greater than 1/2, meaning that M only admits non-diagonal Einstein metrics, and 2 infinite families and 3 isolated examples with A less than 1/2, where M admits diagonal metrics. Recall that we have that G5 is Einstein on any M when h over k is an irreducible symmetric space. So we have 5 more families and 7 isolated examples where the condition about the Killing form doesn't hold, but M admits a unique non-diagonal Einstein metric given by G5. So with this setting, we are going to study the stability type of these metrics with respect to the Hilbert axiom, meaning that we are going to study its stability as critical point of the scalar curvature functional restricted, well, to the metrics of this form, to the metrics in M4 with unit volume. So we have this lemma or this proposition. We found a formula for the scalar curvature on any metric of this form on M. It is given by this equation. Here it is involved, of course, the metrics S1 to X4 and the dimension of the irreducible symmetric space H over K and the dimension of K. So when we restrict this function to metrics of unit volume, we can study the stability type of the metrics. And we said that an Einstein metric is going to be called G unstable if we found a positive direction on the tangent of this manifold for the Hessian of this functional, and it's going to be called non-degenerate if the Hessian is non-degenerate when restricted to the tangent space of the unit volume G-invariant matrix of this form. So for the diagonal metrics, Lauret and Will did the study of the stability, showing that these metrics are both G unstable with different coindexes. That's why these metrics are not isometric. So we are going to do the study of the stability of the non-diagonal Einstein metrics on M. If in the setting H over K an irreducible symmetric space, we have that the H times H invariant metric G5 exists on any M, and it is non-degenerate G unstable of coindex 1. And if we assume the condition concerning the Killing forms and A greater than 1/2, then we have the non-diagonal Einstein metric G3, which is also non-degenerate and G unstable, but with coindex equal to 2. A sketch of proof of this theorem, we consider the normalized scalar curvature of metric of this form, x3 equal to 1. We were lucky because both Einstein metric have x3 equal to 1. They were up to scaling even like that. So this normalized scalar curvature is given by this equation. And we have that these are critical points of it, and we studied the Hessian at them. So in the case of G5, it has 2 negative eigenvalues, and in the case of G3, it has only 1. So that's why we can prove the G unstability with its respectively coindexes. So to show you a plot of this, we consider as an example the homogeneous space M20 of dimension 20, given by SU4 times SU4 over delta SP2. Here, the constant A of the Killing form is given by 3 over 4. So we have that both metrics, both non-diagonal metrics exist here. And let me show you the plots. Are you seeing the file?
Yes.
Great. So for this subspace, for this, homogeneous space, we have the scalar curvature, and we can project it into planes to see a plot. First, we are going to project it into the plane x1 plus x2 equal to 2. This plane contains both Einstein non-diagonal Einstein metrics. So let me check. Here. This is a plot in this case. The blue point is the metric G5. Here we see that the coindex is equal to 1, or at least we have one negative direction. And with this metric G3, it seems like G3, sorry, it seems like it is a minimal of the function of the normalized scalar curvature. But it is due to the projection of this plane. If we consider another plane, for example, x1 equal to x2, we can see this plot where we clearly see that it has a negative direction. In this plane, we only see G3 because G5 does not have x1 equal to x2. So here we can see the coindex of these metrics. And I think I went too fast, but that's all I want to say. Thank you so much for your attention.
Okay, thank you very much, Valeria. Are there questions? I have a question.
Yes.
Among the irreducible symmetric spaces,
Yes.
you have families and also isolated cases, right? That
Yes.
usually exceptionally groups are always involved. Have you noted any difference about something, stability or something about these two different types?
No, they behave the same. Note that in our equations, it's like it only matters the dimension of the spaces, and it doesn't change so much the behavior of the stability. It's the same. I would say it's the same, or at least I do not notice any difference between both cases.
Okay, I expected something different for the exceptional. That's cool.
They are boring in this case.
And what about the isotropically irreducible spaces? Are you interested on these spaces, which is probably the
Or
next step?
Sorry,
Replacing irreducible symmetric, replacing G over K, an irreducible symmetric space by an isotropic irreducible space.
Yes, I think it's going to be interesting, but we do not know if or which are the Einstein metrics on this case. We only have these diagonal metrics studied by Lauret and Will, but the computations are really hard. So we don't know if we are going to be able to find Einstein metric or more Einstein metrics in this case, in those cases.
Okay.
Yeah, these non-diagonal metrics are really Ricci painful, no? It's really like many pages of computation to compute Ricci. And so with Cynthia, we only computed when H over K is a symmetric space, because that was already like 5 pages of computation. And well, then we don't have the Ricci tensor yet, a formula in general.
Okay. Are there more questions or comments?
That was a nice talk.
Thank you, Megan.
If not, we thank again. Very nice talk, Valeria. Thank you.
Thank you.